This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Our speaker today is from UC Davis. He's professoring in Double E. His name is Raj Amirtharajah. I'm sorry, I got it wrong. I knew I was going to do that. Amirtharajah. And he's going to be talking about harvesting power for sensors so that they operate without batteries. Raj.
Thanks. So I think most of us are familiar with the idea of this wireless sensor networks, where basically what we're doing is we're combining sensing and actuation with computation and communication in sort of these little devices, which we can then distribute without having to wire them all together. And then they organize into a little network which communicates data between them, and that can enable a bunch of interesting applications in things like industrial monitoring of infrastructure, creating interactive environments, detecting targets or chemical weapons or whatever for the military, deploying location-based services, or just plain doing some science. And then the issue, once you've deployed this network of 1,000 nodes, say, is that you have to deliver power to it in some way, and you certainly don't want to wire it together. The whole point was for it to be wireless. And it's expensive to have a technician or a graduate student running around and replacing the batteries. So, the issue is not that battery technology hasn't been improving. It has. Capacity has increased by roughly 8% a year or so. But our demand for power consumption, at least in mobile devices, has been growing by 24% a year. And so that gap is certainly getting very wide for things like cell phones and other sort of portable multimedia type devices. The gap is not so bad for sensor applications because of course, you don't need to run your thermostat, say, at 4 gigahertz, your thermostat microcontroller at 4 gigahertz. But there, the issue mostly is that we'd really like to shrink our devices to enable a variety of other applications. And here is sort of where we stand, or the recent state of the art. This is, on the left here, a wireless sensor Mote that you can buy from Motive, a startup out of Berkeley. It's got the radio, it's got some sensors, it's got the microcontroller, et cetera. And the form factor is not so bad. Here's a sort of USB connector on the left for scale. And it's nice and sort of thin and flat until you add the power source to it on the right-hand side. So this one has a solar cell on one half of it, some big storage capacitors on the other half, and some power regulation circuits, and so on. So you can see that in terms of the volume, you increase it quite dramatically as soon as you add where the energy storage goes for the sensor node. And if I look at the numbers off the data sheet, this little device consumes about 70 milliwatts when all of its pieces are active, about 17 microwatts when they're all idle. And as we'll see later, that 17 microwatt idle power is actually not really sufficient for a very long lifetime application. So I think the point of this is that you can see that the power sources contribute at least a significant amount of the volume and the cost to this device. And we'd sort of like to have smaller systems, maybe a cubic centimeter or less, so we can create sort of a more hidden or less obtrusive military sensor. If you want to create an implantable device that you could put, say, in a child or an infant, we have applications where the volume is kind of an issue. And so we have two sort of choices. One is we could reduce the power consumption of the different modules. That will let us run longer for less battery volume. Or we can try to extract some of the energy for our operation from the environment the sensor sits in. And what I'm going to do today is mostly focus on that second option and talk some also about the first and how we sort of can design systems to get energy from the environment and how that impacts or even provides obstacles to reducing their power consumption. So these things can be complementary or they can oppose each other. And what's enabling us to even consider this is that we've done a really good job of scaling the power consumption for sort of a fixed throughput type of problems. So things like digital signal processing, a fully programmable DSP that might have cost you, 10 to 20 milliwatts a few years ago has now scaled down into sort of the hundreds of microwatts, below a milliwatt type of average power consumption. For less programmable, more specialized DSP, you can do more tricks at the circuit and architecture level to exploit energy efficiency. And that has scaled from sort of the single milliwatt region down into the tens of microwatts. And for even lower throughput applications, things like sensors or biomedical devices, again, we've scaled from sort of the hundreds of microwatts now down into the tens of microwatts or potentially below. And so below a milliwatt, then, it starts to make sense whether we can try to use ambient energy sources to power our electronic systems or not. And of course, there's a number of sources available. Solar, of course, is the one everyone is familiar with. You just use some photovoltaic cells to convert light to electricity. And it's been very well established in things like calculators and wristwatches and so on. You can also use electromagnetic fields, typically not stray fields, but fields that you actually create yourself. And this is how our smart cards, our little hand-waving key fob debit things work. Basically use an inductor and a low-frequency EM field to couple into that, and that powers enough circuitry to read a memory. And you can use that to charge your pacemaker or power an RFID tag. You can also explore using thermal gradients. So people have demonstrated systems where you can power a very low power device off of just a temperature difference between the surface of your skin and the air. Or if you want a slightly higher temperature difference, you can poke one electrode beneath the skin and then expose the other to air, get a few more degrees, and you might get on the order of a few microwatts out. And then you have the opportunity to use parasitic mechanical vibrations in the environment of the system. And I'm going to focus on sort of the solar power and the mechanical vibration as kind of two environmental energy sources which I think are somewhat complementary to each other. For solar power, of course, you need light or something, some kind of illumination. But for mechanical vibration, you can use that at nighttime or in places where you're sort of permanently in the shade for things like monitoring machinery, large machines like turbines, engines, machine tools. Every time the transmission makes a revolution or so on, that sets up sort of the gear teeth vibrating, and those parasitic vibrations can be picked up and potentially used for an electronic system. Certainly anything that moves like a vehicle, a ship, a car, or a structure like a wall, staircases, buildings, and bridges. All of these things provide small, low-level vibrations which you could potentially harvest for power. And then the sensor applications demand sort of a long lifetime environments where you don't necessarily have continuous or even frequent exposure to light, say the underside of the Bay Bridge or something like that. Another class of applications then would be something where you actually wear it, like on the wrist or embedded in your clothing, and then it's really the vibration set up by you moving around which provides the power source. And so here's sort of what a system might look like. On the left-hand side, we have a bunch of potential power sources, vibration, solar, some kind of stored element like a battery or a capacitor, some kind of power electronics to provide the interface between these power sources, and then our load electronics, so something like a sensor or an actuator, probably converting that sensor data to the digital domain and using an ADC, some kind of processing of that digital data, and then communication of that data out to other parts of the network. And the idea is that by combining multiple energy scavenging sources, we can extend the lifetime of this entire system beyond the limitations set for battery technology in a fixed volume. And that's sort of half the story. One is how do you design a system to fit within the power available from these sources. The other half of the story is to recognize that you don't get a nice sort of fixed output power from any of these scavenging sources. These can be highly variable. Certainly sunlight varies whether it's day or night. Then the vibrations can vary both in amplitude and frequency depending on where you're getting the parasitic vibrations from. And so to cope with that, we've explored a bunch of techniques which allow us to trade off the power consumption of our digital circuits for the accuracy of their results. And that way, if the output power available from the scavenging sources drops below a certain threshold, it's not like the system dies. The system is still operating. It's just giving you a result that's not as good as it was when it had a lot of power available. And we'll see some examples of that in sort of the second half of this talk. So here's kind of a hint as to where or how much power is available in a cubic centimeter for various energy sources. And on the x-axis here is the number of years of operation. On the y-axis then is the average power consumption over those years of operation, which you can sustain within a cubic centimeter. And so lithium ion, it's a good battery technology. You can run out for 5 years in a cubic centimeter if your average power consumption is somewhere below 10 microwatts. Right? That may or may not be a useful level of power. If you're harvesting energy from parasitic vibrations, then as long as your transducer is working, then and that vibration source is available, you can get roughly an order of magnitude more than that on average. So between maybe 10 microwatts and 100 microwatts within that cubic centimeter. And then if you cover that cubic centimeter with solar cells, then you can get up to a milliwatt on a bright sort of sunny day with no obstruction. But indoors under fluorescent lighting, you might get a couple of orders of magnitude less power consumption than that. Okay? So here we're seeing that having a sort of a suite of energy sources, batteries, vibrations, and solar can give you a range of power levels available over years of operation and within that sort of cubic centimeter of volume. Right, and there's been a few demonstration systems. Here's an example from the Berkeley Wireless Research Center, where basically they created a kind of low power, a 1.9 gigahertz RF transmitter, and they measured how often that transmitter could be turned on or what its duty cycle was as a function of sort of the available solar or vibrational energy. And you can see, depending on the light level, you can actually have sort of 3 orders of magnitude variation in the duty cycle. So under low, dim indoor lighting, it can only be on sort of a fraction of a percent of the time, whereas under sort of outside on a sunny day, it could be on 100% of the time. Okay? So now your system has to be able to decide whether it can operate with this type of duty cycle, 0.36%, or if it has the power available to operate at 100% duty cycle. Now for vibrations, for example, at a fixed frequency, but maybe a factor of 2 difference in terms of acceleration, the amount of power available is much less than solar, right? So you drop that order of magnitude or so. But again, it could be varying by almost a factor of 2 or not. 1.6% duty cycle for the low amplitude vibration or low force vibration. 2.6% duty cycle for the high force vibration. Okay, so there have been a few demonstration projects which indicate that's possible, and now the issue is how do we really try to make this a viable technology. So with that introduction, what I'm going to do then is sort of cover 3 aspects of this energy scavenging work. The first is to talk about another approach to solar energy harvesting, where we try to actually integrate the solar cells. Then I'm going to talk some about mechanical vibration energy harvesting and how you might do it and what the power available might be. Then I'll talk about how you actually design your digital system to operate within those the constraints of the power available and the variability of that power before I conclude. So solar energy harvesting, again, this has been demonstrated a couple of times. This is another implementation, the Everlast Mote from UC Riverside. And they use sort of a typical commercial solar cell. This one's based on crystalline silicon and can provide pretty decent power output for the area, 450 milliwatts. And if you want to lower the cost, you can go to a sort of an amorphous material, either amorphous silicon, cadmium telluride, or some other material, although you tend to lose efficiency. But regardless, in general, people have not been tried very aggressively to integrate these things because they've always sort of assumed that the power you want is going to be too high to make integration on chip with circuits acceptable. In addition, for stored energy, the Everlast Mote has this high density supercapacitor. So you can see, by the way, this is not a misprint. It is 100 farads in something which is a little bit bigger than a quarter, at least in terms of the area. So do not put this on your tongue. You will die, actually. So people have gotten really good at making these high-density supercapacitors as well. But what we want to do is we want to take a look at integrating, how you might go about integrating the solar cell and the capacitor cheaply into maybe just a standard CMOS logic process. Again, looking to decrease cost and volume. And one way to do that is to just say that we buy integrated solar cells every day. We just call them CMOS imagers, and we use them to take pictures. But instead, we can try to think of using them as a power source. And so we took just sort of a very simple N-well diffused into a P substrate, forward biased a PN diode, a simple passive pixel design from a CMOS imager, and said, if we shone light on this, can we get a reasonable amount of power out? And then we played some games which you would not do for a pixel. We actually interspersed fingers of N and P diffusion inside there in order to sort of increase the depletion region area so we can collect those photoconductive currents more easily. And then in order to do the energy storage, we took advantage of an effect that people usually try to get rid of, which is namely the parasitic capacitance between layers of metal on the VLSI chip. Right? So again, this is a capacitor. If we pack in that metal as tightly as we possibly can, the question is, can we actually, and given that we have 9 metals of level available in modern processes and so on, can we pack it in tight enough to give us enough capacitance that it actually might be useful for something? Right? And so we tried sort of a number of different diode configurations. Also, because we were trying to be greedy, we thought we would save the most area by packing the capacitor on top of the solar cell and hoping that it didn't obstruct too much of the light from getting down to the silicon substrate. Okay, so if you do that, there's been some work in the past coming up with various theoretical limits and empirical upper bounds for how much capacitance you can pack into a certain volume for a given CMOS process. And so for the diodes we built, which were relatively small area, something on the order of a few hundred square microns, you can get a few hundred femtofarads, basically, of the metal capacitance. And then you get a little bit more thanks to the depletion capacitance of those PN junctions. Okay, so a few hundred femtofarads can't necessarily store a whole lot of energy there, but if you have a low power circuit, then that might be enough for you to run for a little bit. Right. And so we fabricated a test chip with a number of these different structures of various geometries and so on. And under reasonably high light intensity conditions, so something like sunlight outdoors at noontime, you would get on the order of maybe some tens of nanowatts out of these diodes, which are sort of a few square microns in terms of area. Okay? And you can store maybe a few tens of femtojoules in that capacitor that's sitting on top of those diodes. At voltages which admittedly are not necessarily high enough to run an old CMOS technology, half a volt or so, but of course you can stack a couple of these diodes in series and get your 1 volt or 1.5 volts for a modern process. Okay. And so if I wanted to get sort of 5 microwatts in bright sunlight, and so this is something like how much a lithium-ion battery would need to consume, or you could discharge a lithium-ion battery for 5 years, then it only costs me on the order of a couple hundred microns by a couple hundred microns on a side, which is a pretty small fraction of a typical chip today. So this is sort of a plausibility argument, at least, and a proof of concept that even though the imagers, the N-well photodiodes aren't the best, solar cells, they're at least enough to get you some power to extend the life of your sensor node. Okay. And then to complement that, for situations where you have very low light intensity or no light at all, then you can imagine getting energy from parasitic mechanical vibrations. And there's a big difference, of course, between the amount of energy you can get just by sticking something on a wall and hoping that the wall shaking powers it, versus you actually turning a crank, which is what you can do on a wind-up radio, or shaking a flashlight. You can literally put watts into that thing. But on the wall, we'll find that you can't necessarily get watts of power out. So Shad Roundy, when he was a graduate student at Berkeley, went around and put an accelerometer on a bunch of basically home appliances and office equipment to see sort of how much mechanical vibration is available when these devices are, say, operating. Right, so for blenders and clothes dryers and so on, you can basically see that you're going to get harmonics of the 60 hertz power supply frequency, so 60, 120 hertz, and so on. And then for other things, things like structures where the resonant frequency or vibration frequency is driven by other factors, you might get something on the order of hundreds of hertz. But nowhere do you get something on the order of tens of kilohertz or megahertz. So that's the frequency of vibration, and then that's going to be important to us when we think about how much power might be available from these sources. In terms of the accelerations available at these surfaces, again, you can go from something as high as 6 Gs on, or 2/3 of a G, sorry, on your blender casing to maybe just fractions of a G for things like your heating ducts and so on. Right? So this is sort of the range of vibration sources readily available. And we can model any transducer which converts that vibration to electrical energy using kind of very simple second-order mechanical system model. So our transducer has some mass, it has some compliance, which we model as a spring, it has some damping, part of which is due to the frictional losses and air and so on, but part of which is also the energy we're taking out and converting to electricity to use to power our system. Right? So even though we have sort of this very simple model that can at least give us a handle on to enable us to estimate how much power is available. So if I go ahead and solve the second order differential equations here, and I optimize the maximum power dissipated in this damper, which corresponds to extracting the maximum power out, then I find that I want to run the system at its mechanical resonance, which is a result we should all remember from circuit theory. And the output power is proportional to the mass, proportional to the square of the acceleration, and inversely proportional to the resonant frequency, right, with some fudge factors and so on. And now this is fine, except for when we want to think about how we scale our system down, right? The problem is that if I scale my system to smaller and smaller volumes, given that I only have materials of certain densities available, then of course the mass falls off linearly, so that means the power falls off. The mass falls off with the cube of the dimension, so of course the power falls off as well. And it's worse than that because the resonant frequency is also going up as I scale the mass and the volume down, since it's root over Km. So in both terms here, I'm starting to lose as I shrink my system to smaller and smaller volumes. And so that means that puts more pressure on my circuit design and my load electronics design in order to make this approach viable. And I can model this as an electrical engineer. Fortunately, I can model it as a simple RLC circuit with the inductance corresponding to the mass, the resistance corresponding to the dashpot mechanical damping, the compliance or the spring corresponding to a capacitor. And then I model my transduction mechanism as simply a transformer. And using a simple model like this, then I can estimate power consumption for various forcing functions. So here's one where we looked at how much power you might generate from taking something about the size of a AA battery and maybe strapping it onto your belt and then just walking around fairly slowly for a driving frequency of 2 hertz and maybe displacing it about an inch or so. And then the average power coming out is something like 400 microwatts. But of course it's varying by a huge factor depending on whether you're applying an impulse to that mechanical generator and it's resonating for a while or not. And so given that, and so here's sort of an illustration of what the two constraints are. One is that your average power is in the microwatts that you have available, and that's before you even go through the inefficiencies of converting that to a stable DC voltage. And then you also have the fact that the power output is switching with time constants on the order of milliseconds or tens of milliseconds. So we have to think about how we're going to go about designing our systems to cope with that. Now, a number of transducers have been proposed in the past, worked on by myself and other researchers. Like I said, the one that we estimated 400 microwatts out of is basically like something like your stereo loudspeaker being driven in reverse. So you have a coil of wire, it's attached to a mass and a spring. The whole thing's suspended above a permanent magnet with an air gap. And then as the mass vibrates, that coil cuts a variable amount of flux and induces a current in the coil, which you can then extract power out of. So 400 microwatts out of something about the size of a AA battery. If you want to shrink your device further and you want to use, say, MEMS technology, you can do that. You can basically just create a variable capacitor And if you charge the capacitor when its plates are at a maximum, so when say for example, if these are the two plates of the capacitor here and here, when they overlap the most, the capacitance is at a maximum. I put some charge on there, and then the vibration moves the plates apart, so then the capacitance goes to its minimum. Since charge is fixed and capacitance falls, then voltage has to increase, and that means I'm putting energy into the system. But I can see that as I scale my system from the size of a AA battery down to something which is on the order of a square centimeter plus a few hundreds of microns thick, I drop a factor of 50 or so in terms of the power available. So 400 microwatts down to less than 10 microwatts. And another technology which people have worked on, including some folks in my group, is to actually use piezoelectric materials, which have the nice property that you can create all kinds of fun transducer shapes out of them. Here's just a simple bender with a mass attached to the end. And the idea is that the vibration causes the mass to wiggle up and down, and the piezo material flexes as if it were a diving board. And then as it deforms, then it creates a charge, and you can extract power out of it. Power on the order of a few hundred microwatts for, again, something which is several cubic centimeters in size. Now I have a movie which I'm going to show at least a little part of here, showing some of the transducers that you can build. And it's actually fairly easy just kind of for a hobbyist to build these things. You just need to order some various piezo bars from a number of vendors. Some of them can be made flexible because they're woven. Some can be made very stiff because they're solid. And then all you have to do is clamp one end of them using something as kludgy as some bolts and some metal bars. And then you can put that onto some vibration source and then shake it and then watch the output. And then by playing with the mechanics of it, you can get different effects. For example, having a disc which is clamped at the center allows you, for example, to create a quadrature electrical signal as a traveling wave travels around the size of the disc. And I'll show you a brief example of that. And then if I have time at the end, I'll show you some more examples. But here's basically the traveling wave going around the disk as you drive it into resonance or not. And from a circuit designer's point of view, what's nice about this is one way of maybe generating a set of clock phases which you can use to control the timing of your system. So let's stop that there. So the upshot of it has been that in literature for the past 10 years or so, a number of different transduction mechanisms have been proposed, and more are being developed all the time for a number of applications. But the power output has pretty much been sitting in that sort of few microwatts to maybe a few hundreds of microwatts range. Okay? And again, because of the material constraints and our volume constraints and that equation relating the mass and the resonant frequency of the output power, that's pretty much where you're going to be for all time. And so from a circuit designer's point of view then, now how do I get my system to do something useful if I only have a few microwatts available? And not only that, what happens if those few microwatts go to zero every millisecond or so? Okay. And that's sort of what leads us into the kind of last half of the talk here, which is trying to build a digital system which allows you to trade off power consumption for quality in a way which enables some of this energy harvesting technology to be used effectively. And here's an example sort of where it would fit. The digital processing you might do in your sensor node, I sort of view it as being broken up into a couple of pieces. Right? So here, you have sort of a simple Wheatstone bridge type sensor. You're measuring voltage, say, using an A to D converter, and you want to process that data, say, before you transmit it out to the wireless link. But in order to fit within that power envelope of a few tens or hundreds of microwatts, you probably want to split up your digital processing into kind of two different pieces. Something which is programmable and flexible like a microcontroller, you can use for things which are infrequent but potentially high power. So there's a lot of overhead, of course, in fetching instructions, decoding instructions, moving stuff around that you don't necessarily need to implement all of your processing. So the microcontroller might do tasks like calibrating the sensor or configuring a little coprocessor. And the coprocessor is the one that's doing the bulk of the computation. In other words, it's continuously processing the sensor data, say, for example, filtering it using a matched filter. So every now and then you can decide that something interesting has happened. And the fact that you're continuously running this processor means that it has high duty cycle but very low active power, but you're taking advantage of the fact that you can make an application-specific processor very energy efficient, right? By trading off that flexibility for energy efficiency, then you can sort of realize a more efficient overall system. And so here's an example of how that might interface, say, with the energy harvesters and the power electronics. So let's say your energy harvester is a vibration-based one, which produces some kind of AC, unregulated output voltage. And you also have a backup source for when that vibration source isn't available, something like your battery or an ultracapacitor storing some DC energy. That goes through your voltage regulation block, which produces a power supply for your DSP. Now, one thing you can do, rather than closing the feedback loop for the power supply voltage around the absolute value of the voltage, which is something you're sort of interested in only indirectly, you can actually close it around how fast the circuit is operating. Right? So what we really want out of our DSP is we really want it to be producing a result every millisecond or so, which means we want to clock it at 10 megahertz. We don't care what the supply voltage is for that as long as we get our results. So one way of doing that is we can simply adjust that supply voltage until it just barely meets that throughput constraint. So if my DSP is running slow because it's warm outside, then I can run my supply a little bit higher. If it's cool outside, then maybe my DSP is running a bit fast today, so I can decrease that voltage and make it run at the same frequency but with less power dissipation. So I can close this loop around frequency instead of voltage, and by doing that, allows me to basically eliminate all the analog circuits inside the voltage regulator to an extent. I can do an all digital implementation of this voltage regulator, which I know how to make that a very low power circuit. And even if I go through all that rigmarole though, the fact is that if you only have tens of microwatts available, it still costs you a few microwatts to generate a DC supply, right? So in general, the efficiency is still limited, even for a fully digital implementation, to between 30 or 70%. So you're dropping between a third to 2/3 of the power through the voltage regulator, and so now your 10 microwatts becomes 3 microwatts for your DSP. Now, how do I go about enabling that trade-off where I can use less power to produce a lower quality result and more power when it's available to produce a higher quality result? Well, I can use that microcontroller to control a bunch of configurations for my DSP block. But now I know that anytime I have reconfigurability into my system, that added flexibility costs me overhead in terms of circuits, area, and power. So what I want to do is I want to be able to create this set of configurations with as little overhead as possible. Now the advantage is that people have shown that you can get roughly 60% to 200% improvement in the lifetime of a system by being able to operate it at configuration 0 for the parts of the time when low power is available. And similar gains can be expected in the energy harvesting scenario as well. So now one approach then, so you want a low overhead approach to creating a number of different configurations. So something you can do is you can go back to some of the earlier digital design techniques and think about using serial computation instead of parallel computation. Right? So serial computation allows you to trade off accuracy for power quite directly. In fact, at the single bit level, all you have to do is shift in fewer numbers of bits as you do your serial, say, addition here. Now, if I compare that to my parallel adder, where I'm computing a whole bunch of bits in parallel, then I can see that, of course, it uses less area because there's fewer devices, less interconnect capacitance, which is kind of an increasingly important factor in terms of total power for a chip. But even more important, since there are fewer devices here, there are fewer devices which can be leaking when they're supposed to be turned off. And since leakage power is such an important component of chip power dissipation today, then minimizing that leakage power is very important. On the other hand, if I want my result out at a fixed throughput, say every millisecond or so, then I have to clock my serial adder at a much higher frequency potentially than my parallel adder. So if I clock it higher, then that means I dissipate more dynamic power by switching these capacitors more often. And I potentially have to run at a higher power supply voltage. So between these two computation approaches, there's basically a trade-off between dynamic and static power. The parallel approach will have less dynamic power, but the serial approach will have less static power. And then the question is, at what frequency do we switch from being dominated by static power to being dominated by dynamic power? And it turns out actually that those frequencies are of interest for some of these sensor applications. So here I've plotted power versus throughput or frequency for multipliers, both serial multipliers and parallel multipliers, at a number of different CMOS technology nodes, 130 nanometers to 70 nanometers. Solid line is the serial case. The sort of dashed line is the parallel case. And I can see at low frequencies where I'm dominated by leakage power, then of course the serial technology, serial approach is less power because there's just fewer devices to leak. On the other hand, as I scale frequency up, then of course the dynamic power takes over, and then at some point there's a crossover where the parallel implementation is less power. And then what's interesting is that these crossovers happen at frequencies which might be useful. So 100 kilohertz here at the 130 nanometer node, and then because leakage is growing as we shrink in process size, that crossover frequency goes to a few megahertz, or a few hundreds of kilohertz in the 100 nanometer node, and then maybe a few megahertz in the 70 nanometer node. Right? So these are clock frequencies which are potentially useful for things like microcontrollers and DSPs for sensors. Of course, they would not be useful for decompressing your HDTV video stream. Right? But you can do pretty well with your biomedical device with a few megahertz clock frequency. And then one way you can leverage this property of serial computation is to use techniques like distributed arithmetic, which kind of gets you better area efficiency on your chip compared to just doing all a purely 100% serial implementation. Distributed arithmetic is basically a technique for implementing a vector dot product, which is the same as an FIR filter, where you multiply the filter coefficients as one vector, and then a vector of input samples as a second vector. Now, normally what I would do is I would take each filter coefficient, multiply by a sample, and add it to the next filter coefficient, multiply by the next sample, accumulate that sum to produce my output sample. But I can rearrange the computation because it's linear, and instead of taking it sample by sample, I can take it bit by bit out of each of those samples. So what I do is I pre-compute all possible combinations of my filter coefficients, say they're A0 through A3, multiplied by either 1 or 0. Those are the bits, of course, which correspond to the binary representation of my input samples. If I store all those pre-computed results in this lookup table, then by simply taking a bit slice through my vector of input samples and using that to address the lookup table, I can pull out the appropriate pre-computed result. And then I can just accumulate that pre-computed result to get the same final filter result as I would have gotten by doing a multiply and accumulate in the traditional manner. The advantage I have here is that, again, this is sort of a bit serial process. I can start with the most significant bits of my input samples and then keep going down to the least significant bits. And if I do that, and if I stop the computation before I shift in all of the data bits, then I end up creating an approximate version of the final result, okay, corresponding to truncation of the least significant bits. At the same time, I end up decreasing the power consumption because I've clocked the input bits, fewer numbers of input bits into my system. So here's a way of exploiting that serial arithmetic property in a way it's a little more area efficient there's a little bit more area efficient, but still doesn't give away all of the advantages in terms of leakage and so on. And so we implemented a version of this in a chip that had a microcontroller and a coprocessor for biomedical monitoring. Basically, the coprocessor implemented in a very energy efficient manner the matched filtering, and every once in a while we'd wake up the microcontroller to process the output of that filter and decide whether something interesting had happened or not. So this chip, for this application, we could get away with clock frequencies on the order of maybe a few kilohertz, 1.2 kilohertz for the coprocessor, 250 kilohertz for the microcontroller, with a microcontroller duty cycle of maybe just 1% or so. Now, compared to the power available from that variable capacitor MEMS device, which we sort of predicted would be 4.3 microwatts or so after the power electronics, this particular chip for this application consumed under a microwatt, about half a microwatt or so. And so clearly there's actually some room to actually add more functionality and fit within this power budget of 4 microwatts or so with this sort of aggressive DSP microarchitecture. And in terms of energy efficiency, you do sort of even better. To produce a single output sample for this chip, took about 27 picojoules to compute. Computing the same algorithm on a microcontroller in the same technology, which was the strong arm, a low power microcontroller at that time, took 11 microjoules. So another 6 orders of magnitude more energy than the DSP chip. But where that 6 orders of magnitude came from was the fact that the strong arm is actually 5 orders of magnitude faster, potentially. You can run at 100 megahertz instead of 1 kilohertz here. And that's sort of the important trade-off which we can exploit as circuit designers, is basically that performance and energy efficiency tend to oppose each other pretty dramatically. Getting a 10% performance gain at the edge of your CMOS process can imply maybe a factor of 2 increase in terms of energy per operation. Whereas if you're only operating at a fraction of the potential of the technology, then you can get away with very high energy efficiencies. So we're extending that concept. Basically, we're taking that original distributed arithmetic unit and we're recognizing that you basically have the pieces to perform a number of different serial computations. You have a lookup table, you have a shift memory, which you could think of as a register file, you have an adder, which you could potentially think of as an ALU, and then a little bit of multiplexing and breaking up the accumulator. And you sort of have the potential to implement a number of serial computation algorithms, like serial multiplication of complex numbers, and so on. And that can enable you to implement more DSP algorithms for your coprocessor than just a simple FIR filter. And then you can think about how you want to implement all of these individual pieces to make them more energy efficient. One thing you can do for this memory, which is used to shift in those bits for the input samples, is instead of using flip-flops, you can actually try using an SRAM. And the advantage of that is that you get rid of some of the clock routing, you get rid of the sort of the master-slave latch configuration. So you can decrease area and potentially decrease power and allow you to gate the clocks at a very fine granularity. And the way you make that work is you create an SRAM which has bit lines running both vertically and horizontally. So unlike a traditional SRAM where you only read data out in one direction, for this SRAM you read data out in both directions because some of that data is used to, some of those bit lines are used to bring data into the system and then bring it out to some other receiver. But the other bit lines are used to shift that data along so that you can address different rows of the LUT. And then building it is not too much different than a multiported register file. In fact, it's exactly the same. In this case, your 2-inverter SRAM cell has 2 write ports, one corresponding to the vertical direction, another corresponding to the horizontal direction. And it also has a couple of single-ended read ports, again, one corresponding to the vertical direction, the other corresponding to the horizontal direction. And in fact, in our case, we have a second one corresponding to the vertical direction that allows us to treat this more as a traditional register file. And you give up a little bit of area by having some buffers here to support driving 3 loads at the worst. But if you compare it to the flip-flop implementation, it turns out that you get about an order of magnitude savings in terms of the power dissipation for most numbers of bits. So again, what we want to look at is we want to look at the power as I scale the number of bits that I use to shift through this memory. Of course, I want that power to decrease. That provides part of my energy scalability. But then I also want a pretty low absolute power, below 10 microwatts, so I can fit within the power budget of my energy harvester. Now, the disadvantage of using these lookup tables, of course, is that the more inputs you use to address them, then every time you add an extra input, that means the table doubles in size. So it grows exponentially. So if I have to implement a large filter or a large computation, I'm going to end up with an exponentially large table, and of course that's not going to fit in a reasonable chip area. Fortunately, since the operations can be linear, FIR filtering can be linear, I can just split up that computation to a number of distributed arithmetic little blocks, and then all I have to do is sum up those results to perform my final output. Now, if I take a look at this, and if I think about replacing each of these little vector dot product units with something a little more flexible, can do more than that single operation, and moreover, if I think about replacing each of these adders with something which also can do more than one operation, I see that I have a fabric onto which I can pretty much map a DSP flow graph for an arbitrary computation, at least within what operations are supported. And that is potentially allows us to do something both energy scalable and energy efficient in order to support the work of the microcontroller in a given sensor application. So my students are actually, as we speak, laying out the test chip for this. Each of these tiles has an energy scalable set of linear and some nonlinear functions, things which are useful for some communication, demodulation, and so on. And we connect them with the kind of reconfigurable interconnect that you might see in a DSP, so sort of an island-style reconfigurable interconnect with just enough wires to enable the realization of a suite of DSP applications like FIR filtering, FFT, and so on, with the various switches and connection boxes implemented using sort of full transmission gate technology. Again, these are different choices than you would make for an FPGA, basically because we kind of have a different set of trade-offs than a traditional FPGA. Although interconnect power has to be minimized for any application, the fact is our tiles are much more coarse-grained, have a lot more logic in them than the standard tile of an FPGA. Since that's the case, then we can afford to potentially play some extra tricks or have an interconnect fabric with a little more overhead than we would for an FPGA, just because there's so many fewer wires in our system than there would be for, say, a Xilinx chip. So we're taking advantage of that fact to sort of improve the robustness of the communication. But some things that you typically do for low power interconnect, you sort of can't do in the energy harvesting context. For example, it doesn't make as much sense to create a separate power supply with a low, even lower voltage, so you have low swings between zeros and ones on your interconnect, because those power supplies tend to be about 50% efficient or so. Right? So you're pretty much stuck with high swing signaling. So the way you go about decreasing the power of your wires in this context is you try to minimize the capacitance you're switching. So one way you do it is something you would never do in an FPGA, which is you actually space the wires out in a non-minimum pitch, and so you decrease the coupling capacitance between them, which is pretty significant in today's technologies. And then you might do things like recode the data a little bit so that they don't transition as often and switch that capacitance. And this allows you to create or implement this trade-off. So here's just an example where we simulated the power consumption and the recognition performance for a particular DSP algorithm. So this algorithm was designed to detect biomedical events. So basically it was an acoustic heartbeat monitor. And the red curve corresponds to the accuracy with which I did make that detection, so the number of the true positives. And the blue curve corresponds to the power consumption of the filter doing that detection. Right? And then the axes, the recognition percentage is on the right, power is on the left. And this was simulated at a much higher frequency than what you would typically use in operations, so hence the power is sort of in the milliwatt regime here for illustration purposes. As you can see that as I scale the input data bit width down from 16 to 8 to 4 to 2, then the power consumption falls off. That's good. And then the recognition performance actually falls off, but not quite so badly. So maybe a 96% accuracy down to 95 or 90, a little above 96, a little below 96, down to 95, and then it drops off down to 86. Right? So this is sort of the kind of trade-off curves we're trying to implement in our system with minimal overhead. And you can see that because of some of these nonlinearities, you might prefer to operate, say, at very low resolution, 4-bit quantized data, you still get pretty good recognition accuracy. And that's very dependent on the particular application which you're implementing. And as I said, we're working on sort of a full custom implementation of those individual tiles, really trying to leverage the SRAM design as much as possible, both for the shift memory, the lookup tables, and even for some of the other places where you might typically use a flip-flop. Again, one problem with using flip-flops is they all need clocks, and if you want to vary the number of bits, then that means you basically have to create a clock line with an AND gate for every single bit in your data path. The advantage of using an SRAM is you sort of already have that thanks to the word lines and the decoders there. And it turns out that you can simplify the logic of doing that in a way which makes it competitive with fine-grained clock gaining. And then finally, another project which we're just in the process of wrapping up is to actually think about going a step further and simplifying that voltage regulation process entirely. So as I said before, it is something like 30 to 70% efficient. So what you can do is you can think about, I'm paying a lot of overhead to convert that AC to AC voltage from the energy harvester to DC from my DSP. Maybe I should just try to use the AC supply directly. Okay. And one way of doing that is to get rid of all the active circuitry inside your voltage regulator. Just use a standard full wave rectifier with a minimal amount of filter cap. Again, that filter cap can consume a fair amount of complexity and volume. And then what we're going to take advantage of is the fact that this frequency coming out of the energy harvester is really low. 60 hertz, 100 hertz, kilohertz at the most, right? And at a kilohertz, that's a 1 millisecond period. A millisecond is forever for a modern CMOS process. So I can run my, even as old as a 0.18 or a quarter micron process, I can do hundreds, maybe thousands of cycles of computation in that millisecond. So now I just need to design my chip in such a way that when the supply voltage coming out of my energy harvester gets above a certain threshold, I can start running, and I can run in a way which meets the timing constraints. And of course, I can do that just by using a simple self-timing technique. I create a ring oscillator on my chip, which replicates the slowest part of the critical path between any two flip-flops with a little bit of padding. And then that ring oscillator period corresponds to the delay between the two stages of my two registers in my pipeline. And as long as that oscillator tracks pretty well with the other circuits on my chip, then I pretty much guarantee that that period is going to make my circuit meet timing over a wide range of voltages available. Right, and so here's a simulation of that done at a much higher frequency so you can sort of see it more clearly. The idea is that the rectifier output basically looks like the absolute value of a sine wave, rising to peaks and dropping off to valleys. The self-timed data path for the DSP basically turns itself on once the input voltage becomes high enough. The oscillator runs for a while at a frequency which varies according to the available supply voltage, and then when it drops below a threshold, it turns itself off. Now over here, you can see that the time at which it turns on, this is just the ring oscillator by itself, is not really consistent. So what you really want is you want a circuit, basically a power on reset circuit, with a time constant that's fast enough to be turned on and off at a period of, say, a millisecond or half a millisecond or so at the highest frequency. The other thing you need to do is once the chip turns off, it's kind of a bummer to lose all your state until the next time it turns on again, right? So you want to be able to hold on to that. And if you use an SRAM, which requires power to be applied to remember that data, then you can pretty much be hosed once the power supply drops below a certain threshold. Now, we're fortunate in that the time between these two cycles can be limited to maybe a millisecond or a fraction of a millisecond or so. It turns out that's roughly the refresh period of a DRAM. So we can use a DRAM cell to hold on to whatever state we want to remember between power supply cycles. And then the challenge is getting a DRAM onto a commodity logic process. So it turns out instead of using a trench cap and a 1T cell, you can use basically a 3T DRAM cell. You trade off the area, but you get you actually get something low cost. So we put together a test chip with those features, basically a passive full wave rectifier using MOSFETs, a fast time constant power on reset circuit, a critical path ring oscillator with an enable controlled by that power on reset. And then just as an example test circuit, we're building an energy scalable, of course, a distributed arithmetic block built with a combination of flip-flops so we can look at their state retention properties when the power supply drops below threshold, as well as built out of these 3T DRAM cells, which we're planning on holding on to that data for multiple cycles. So here's the layout of the chip. It's actually built and tested, and we have measured results, but since they're going to be published in a couple of weeks, I sort of can't show you that because the IEEE will get on my case about it. But it integrates the on-chip MOSFET rectifier, which is up here, and again, because our power consumption is so low, you can get away with a pretty small circuit. It only has to supply microamps of current. Sort of the analog circuitry, the power on reset, and the ring oscillators and stuff are kind of up here, and then the DSP block, including the 3T DRAM memory, which are these guys, is over here. And this one had about 135,000 transistors and 180 nanometer CMOS. And it turns out that you can build, it's a big DRAM cell. It's on the order of 10 square microns, something like that. That's just about the right size to combat the leakage in this 180 nanometer process for an input supply cycle of a 60 hertz frequency or so. Okay, so let me wrap up there, and then I have a few minutes left, so I can go back and show you more of that movie. So this energy harvesting for wireless sensors, the reason we're getting away with it is basically because not really demanding a whole lot of performance out of our sensors, especially on the digital side. And even on the RF or wireless side, we're pretty much asking for low data rates and not having them be turned on very often. Okay? So once we get our average power consumption down into this milliwatt, sub-milliwatt to a few microwatt region, then it becomes possible. And you can use either solar, thermal, or mechanical vibration. But all of them have problems that there becomes a challenge to scale down below a cubic centimeter. Both the solar and the thermal ones are sort of proportional to the surface area you have in contact with either light or your temperature gradient. And with a mechanical source, of course, it's just that the output power scales poorly with the mass and the resonant frequency. So either way, if we want to think about scaling our system down in size, the energy becomes limited. And of course, it's highly variable. Even solar power varies by a few orders of magnitude depending on lighting conditions. And that variability impacts all parts of the system. You want very simple power electronics with as few analog circuits as possible. And you want energy scalable design in your processor, as well as sort of rethinking how you might architect things at the microarchitecture level. So reviving things like serial computation for the energy scalability, doing self-time design to cope with the supply variability, and so on. And so, I think that this is a pretty rich area to be working in. Of course, I wouldn't be in it if I wasn't. There's a number of opportunities looking at things like transducer designs and modeling, co-designing the power electronics along with the transducer, and then thinking about how we might get our mixed signal circuits inside these power budgets as well. Of course, analog circuits are more difficult to get sub-microwatt analog circuits, although the digital wristwatch guys have done, or the crystal wristwatch guys have done a good job of that years ago. But especially in this context of having a variable power supply voltage, you need really good power supply rejection, for example, in your analog circuits. So let me just wrap up by acknowledging the work of my graduate students, collaborators, and the people who write our checks. And they've all contributed to multiple parts of these projects. And then I'll show you a couple more examples out of this movie. Actually, hopefully it'll. Problem is I don't know how to fast forward through this thing. But and the other problem is my students like iMovie too much, so they have all these little slides and all this other stuff going on. As I said before, there's a number of materials available. Even though piezoelectrics are ceramics and stiff, people have woven them into these very flexible types of components. And then later on in this movie, I can show you some of the various vibration modes which you can get by exciting these flexible bars. It turns out that mechanical systems, I was a little bit surprised by this, can have really nice, really high Qs you would sort of kill for in your RLC circuit. Especially something two-dimensional like this disk here. At some of these resonances, we're getting Qs easily in the tens or hundreds. And so what you can potentially do with that is, rather than just using it as a power production element, you can also think of it as also an energy storage element. So a high Q mechanical system, like a flywheel, say, you can imagine storing energy in it, as well as storing energy in it. And then as long as the Q is big, then you're not going to lose too much to the dissipative effects over time. So that's something else we'll probably take a look at later on. So again, this is looking at the traveling wave mode around the bar, and again, around the disk, sorry. And with the disk divided into 4 quadrants, you can get kind of a quadrature. It's a little bit difficult to see, but there's roughly a 90 degrees phase shift among those. It's probably easier to see in the second plot here. It should be shifting soon. Maybe it wasn't so easy to see. Like I said, the advantage of using the disk is not just that it's high Q, but also that you have potentially these multiple electrical signals which you can use in your electrical design. So here with the flexible bar, you can see again sort of modes where you have a node here, an antinode here at the clamped end and at the free end with the mass on it. And all these modes, because they have different resonant frequencies. Again, here's one where the antinode is out here at the end, and well, this end has to have a node because it's clamped. What's nice about having these modes where there's different frequencies is that since you don't know what the vibration frequency is necessarily, it could be varying here and there. By having a structure which has multiple mechanical resonances, then you could potentially obtain power at a number of different vibration frequencies, and you don't have to necessarily know at design time exactly what the vibration characteristics are. As I said, we're using a flexible, a very compliant bar, and a very long one here, so you can sort of see what the different modes are. But of course, in a practical system, you would use sort of a much smaller scale device. So I'll just stop that there. And I'll be happy to answer some questions. Thank you very much for your attention. Yes?
These geometries are ancient history. Do you have any trouble finding access to fabs at half micron?
Actually, no. Well, for example, Moses still offers sort of half micron technology. So actually, that half micron chip is really from many years ago when it was my PhD project. So that's not a recent one. But it turns out that 0.35 is pretty readily available because they tend to offer a lot of high voltage devices there. Things that you would.
10 years out.
Right. Yeah.
Obviously, to continue that question, apples to oranges, this stuff's not going to come forward.
In terms of technology.
Yeah, I mean,
Yeah.
you bring it forward, a lot of your assumptions break.
Right. Yeah. So. So that's one that I think sort of has to be answered in the application context. In other words, I think that for a lot of these devices, you simply don't go to the deep submicron, and assuming the volumes are there, people say that this market is going to be huge, then potentially people will still run your quarter micron fab to support that market. I talk to people at places like Smart Dust and so on, and they do quarter micron designs, thinking about 0.18, not thinking beyond that. And I think basically leakage is the killer. So unless you can, so unless someone tries to create a 65 nanometer low leakage technology, which of course is physically not really plausible, we're pretty much just not going to go there, I think. So.
Well, I think that one of the things that we're going to see here is much greater dependency on asynchronous self-timed circuitry, because you don't have to clock everything every time, so you don't have quite the power dissipation, but you may have more devices. And the number of devices is particularly important because you're much more interested in low power and stability in a power variable environment than you are functionality.
Yep.
And it's nice to know there's a market for all those old fabs.
For the sensor application, RF power, is that shrinking down with new technology, or is that?
Not really. I think so. If you want to get a bit over a certain distance, I mean, you just have to put so much power into the air. That part isn't really changing. In fact, things are sort of getting worse because a lot of the bands that the FCC is giving up for this, of course, things which are crummy for propagation, which is why they're not used by the military or the broadcasters. Beyond the, I think what is happening is, and this might drive at least, to go back sort of to your first question even, there's a bit of an issue with the fact that if you want to do your CMOS, your RF and CMOS, it's sort of nice to be at kind of 90 nanometers or so. On the other hand, you don't want your digital logic at 90 nanometers because leakage will kill you, right? So, do you do system in package? How do you get around that? But the other thing is that it's not clear, at least to me, and I'm not an RF expert, but just looking at what's going on, it's not clear that even for the RF stuff, you really want to get into deep submicron. Again, because for the sensors, the data rates we're talking about are pretty low compared to what people want for streaming, multimedia and stuff. So if you're talking a megabit per second or 10 kilobit per second and so on, again, you can do that pretty readily in 0.18 micron. And yeah, okay, you give up some efficiency in the PA and potentially in other places, but if you can integrate that with your logic, then you're probably happier to do that than to try to do a multi-technology solution there. The other thing that I think is interesting is that, as sort of a digital circuits guy, I always think, people want more computation usually, right? Or in some contexts. But in the biomedical space, for example, I went to a talk where a guy who did hearing aids was asked, he did his design in 0.35 or some old technology, and someone asked, well, why don't you go to better feature size so you can get more digital stuff on there? He basically said, we don't know what to do with it yet. The biophysics isn't solved. The medical applications aren't quite there to know what they would do with the extra transistors. So that's sort of another reason why I think that some of these older fabs will stick. As long as this market is big enough, I think people will try to supply it. So, yes.
Can you tell any status and commercial application of these technologies?
So what? Well, for solar, obviously, there's a lot of stuff. For vibration-based energy harvesters, there's between half a dozen to a dozen sort of startups that are doing this. Some here in California, a couple in Boston, and then some more in the UK. Almost all of them have gone with the, is that true? Most of them have gone with the electromagnetic idea. So you have a permanent magnet and a coil or some kind of variable flux linking mechanism. Mostly because people know how to build that fairly well, because people can make miniature permanent magnet loudspeakers, and it's quite a similar technology. And also you get current out at reasonable voltages. The problem with piezoelectrics is that you get high voltage but very little current. And that's okay for some applications, like sort of the research application that we're doing here. We're talking about microwatt power dissipation. But if you want to run your TI microcontroller, which needs still a few milliwatts these days, kind of the magnetic one is the technology to use there. But commercially, there are people who are selling this stuff. I think the Navy has a few SBIR, STTR programs for wireless sensor networks for ship monitoring, which they've farmed out contracts to various startups. The other place where people are starting to see some of this stuff is in tire pressure sensors, actually. So there's some regulation within some number of years. Your car is supposed to be monitoring the tire pressure, and the idea is that you put your pressure sensor in the valve stem, and as the wheel rotates, it comes in contact with some antenna, attached to your car, transmits its data at that point, and then goes around at a revolution, and so you get pressure data, at the speed the wheels are turning, and then what's the power source for that? It could be a battery, but you have a lot of vibrations available, so some people are looking at a little moving coil transducer for that. So I can put you, if you want to send me an email, I can email you a list of half a dozen companies or so which are pursuing this. But they all seem to focus on this one transducer technology, which is already available pretty readily commercially. And the things like the MEMS stuff and the piezo stuff is probably further out as far as getting into the marketplace.
In the 60s, people built radios for distribution in the eastern countries, which basically were driven off energy captured by a resonant circuit into the local radio station. Is there enough power there to do that? Is this a practical mechanism for driving things here?
Actually, I think it is if you're close enough to the transmitter. Yeah, exactly. Yeah, I mean, you know, a crystal radio is an existence proof, right? That you can get enough power to at least hear something, right?
Crystal radio driving a magnetic headset is an existence proof, I would argue. Though I don't know what the local environment provides in terms of radio signals here. Certainly, AM band radio, you could probably build an antenna that would capture most of that, and then use that to drive a power supply.
Yeah, yeah. No, I think it's quite feasible actually. So again, it all depends on distance to the transmitter.
And the C system specifications requiring more noise and vibration in order to power the sensors.
Yeah. Yeah, that'd be interesting.
Your work is on the mechanical stuff, but the RFID stuff seems to be kind of gaining momentum.
Mm-hmm.
So, I mean, illuminate and interrogate is where they're going for the sensors, at least.
Sure. For the RFID tags, yes. Yeah. They are. I think right now, most RFID tags are very simple. There's some flash memory and a power converter.
Look up and down.
Yeah. Now you could if you want to do some processing there and some sensing there and so on, you could certainly there is enough power available to do that for while it's illuminated. And I imagine people will start looking at that more seriously. But at the moment, most of the work I've seen there is let's read the bits out. And that's about it.
When you had your diagram that showed a passive, or effectively a rectifier,
Right.
That could be another way. I was surprised you didn't incorporate the ultracapacitor into the rectifier as a post-low-pass filter.
Yeah, it probably should be there actually.
100 farads is an awfully big filter.
Yeah.
That brings a question. I'm not familiar at all with this new technology. I'd love to get an idea of what it's based on. And second, does it have temperature cycle lifetime like batteries do?
Actually, I do have. Yeah. So these ultracapacitors, there's kind of a number of technologies. Some of them are just sort of different ways of fabricating the old ones, ways where they've sort of found a nice way of basically packing in a lot more surface area within the volume, thinner dielectrics, all that stuff. Some people have looked at using some nanomaterial type stuff to get you there. I don't have the numbers off the top of my head, but I believe that again, there's trade-offs in terms of volume and density and so on. Their stability is competitive with batteries, but not quite there yet. I think the issue is that at least the highest density ones tend to have the worst ESR, so series resistance. So even though you have a lot of energy there, you really can't take a lot of it out at once. That being said, we did some comparisons to the interconnect parasitic caps that we were thinking about on chip, and an ultracapacitor is certainly many orders of magnitude higher than that. So I think that's again a technology that is going to be used a lot, especially in these wireless sensor applications, where you don't need to take a whole lot of current out at any given time.
One of the main uses is SRAM backup.
Yeah. So they're used for that, and then scaled up, they're potentially used for hybrid vehicle applications. Yeah.
Anybody else? Any other questions?
A lot of the RF work on the pages of is complicated DSP spread spectrum, which is evil if you're trying to use the spectrum and don't want that stuff in your way. Great for PhD thesis and things, but it takes a lot of power. I mean, the receiver takes a lot of power there.
Yeah.
What are you guys using for the RF side of things?
Well, right now we're pretty much not doing that part of the work. I have a couple of students who are looking into that. The issue is if you look at the academic work and energy efficient radios, they pretty much go, for these sensor applications, they pretty much go to sort of the simplest modulation scheme possible, on-off keying, for example, or that's sort of the simplest. There have been a couple of demonstrations from groups at MIT and Berkeley that you can do that with reasonable output power, maybe half a milliwatt at the receiver to demodulate and recover data from an on-off keyed bit stream at like a kilobit per second, 10 kilobits per second at 2.4 or 900 megahertz in those bands. And then there's been actually a reasonable amount of academic work on circuits to do that efficiently. I think the issue is that given all the other junk that's in those bands, I'm not sure that that's actually practical. So, ideally, if you had your choice, you would like to have sort of a simple on-off keyed radio in a band where things propagate nicely, for long distances, and then you can use you can almost use a crystal radio type receiver, half-wave rectifier to direct convert to DC, and then a simple digital circuit to sample that stream. Actually, I have a student working on a project looking at that. But I think it's probably not going to be practical given all the commercial interest in these bands to sort of do that. So in some sense, some of this academic RF work in the sensor network space, I'm not sure that it has a lot of longevity because you can't you can't compete with all the people who want to use the spectrum for high data rate type things. That being said, again, DSP has done a good job of scaling as far as energy efficiency with technology, and until we started hitting this leakage problem. That's part of the reason why we can get these complicated DSPs in our cell phones and so on today to do all this demodulation stuff. Whether that's going to fit within these power envelopes is, hard to say. But what people have proposed is the following: is that they propose that if your sensor network, for the most part, just barely needs to be listening, am I being accessed, right? You could potentially do that on a sort of a side channel with very low throughput and very low average power consumption, but it's on for a long time. And then when you actually want to transmit or receive real data, once you hear on the side channel that, I'm being accessed, let me ramp up my, heavy duty, high power block for a short period of time, use that to demodulate my packet, and then turn that off as soon as possible. So that might be one way in which we get some of this technology to fit within all the other competing uses of the spectrum. It's basically really aggressively duty cycle that high power piece and enable that duty cycling with very low power piece on kind of a side channel.
Building monitors, we're talking, once a minute is a high data rate.
Right, exactly. Yeah.
Once an hour is more likely.
Yeah.
We had a speaker whose last name I believe was Braun a couple of years ago who talked from Georgia Tech, who talked about his PhD work where he had a distributed sensor network, and the innovation, at least one of the innovations, was that the sensor network nodes communicated with each other, and then they were DSP processed, and the primary heavy-duty communication from thousands of nodes was pre-processed and then set up pre-computed. And so the overall power cost of doing the transmission was reduced. And it's a pretty interesting talk. And that's online, and you can find it by looking in on the class website. The sensor network issue is, I think, going to become ever more important. There are those who have argued that we're in the decade of sensors as opposed to the decade of high-speed microprocessors right now, and I tend to agree. In any case, thank you very much, and if you have further questions, you can go down and ask them directly. Thanks very much.
Thank you.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.